All right, let's take a look at another CSES math problem, throwing dice. So what's going on here? We want to figure out how many ways there are to get n by throwing dice. That is by adding numbers from 1 to 6. So to get 10, you could do 3, 3, 4. You could do 1, 4, 1, 4. You could do 1, 1, 6, 1, 1. And in particular, they're counting sort of different orders differently, right? So like 1, 2 is different than 2, 1. So we get n. We want to calculate modulo of something. And in particular, n, so the interesting part of this problem is that n is 10 to the 18. So that's very big. We can't do anything linear time. We need some kind of sublinear, probably even logarithmic time solution. And in fact, that will be possible. So the first thing we should do is we should figure out how we could calculate this in linear time. And there's actually a pretty sort of straightforward recurrence. Right, the number of ways to get n, well, the last row could be anything from 1 to 6. So the number of ways to get n is just the sum of the number of ways to get n minus 1, n minus 2, all the way up to n minus 6. And why is that? It's because, maybe it's easier to think about the first row. The first rows are 1, and then there's, anyway, you get n minus 1. You just throw it. Once you have n minus 1, you throw another 1, and then you're done. That's a way. And the same thing for 2 through 6. So this is actually very similar to the Fibonacci problem, the previous video, except that instead of n is n minus 1 plus n minus 2, it's n is n minus 1 plus n minus 2 all over to n minus 6. So let's do that. I'm just going to write this out. Right, so get a little bit lazy. So we're going to have dn is like our state vector. It's going to be dn minus 1, dn minus 5, I guess. And then m is going to be some matrix with the property that n times vn equals vn plus 1. Right, that is vn plus 1, vn minus 4. Okay, so to figure out what m is, just remember that the way that matrix multiplication works is it's a dot product. It's the rows of m times the column of vn. There's only one, which is just this. So the way you get dn plus 1 is you have all 1s in the first row, right? And by the way, m is going to be a 6 by 6 matrix because Vn has 6 elements, so the row dot column, you need to have 6 elements in your row to dot with the 6 elements in the column, and you want to produce another 6 elements, so you need 6 rows to do that. So the first row is going to be all 1s. There should be 6 1s. This is 5 1s. That gives us dn plus 1. How do we get dn? Well, that's easy. You just actually read it off. It's all zeros. How do you get dn minus 1? Well, again, it's just one of the elements. And in fact, you can see that we have a pattern here, right? We're just reading off, subsequent elements. And that was 6 rows. And so we actually don't read off the last element, which makes sense, right? Because we don't care about dn minus 5 anymore. So we could have written code to generate m, but it's easy enough for n equals 6 to just do it by hand. All right, and we should actually, maybe filling out p is slightly trickier, so let me just calculate the first few values. So how many ways are they to get 0? I suppose it's 1. Right, we just do nothing. So I'll do a linear time, linear to 10, to bootstrap it, and then we can go from there. So what am I doing? Right, so dn is dn minus 1 plus dn minus 2 up to dn minus 6, and we'll just say that like the negative numbers are 0, or like d2 is just d1 plus d0, because you can't roll a 3 and get to d2. So that's what this is doing. So I'll say if n, no, it's probably a little bit naughty of me to use n, because that was what I was using for the input, so fine. Okay, so if n is really small, then we can, just use these bootstrap values, and otherwise we can do the matrix multiplication thing. So the point of sort of bootstrapping this was we wanted to sort of have the initial value for our state. Actually, I suppose we've just argued that it's not really necessary, because we can think of the negative numbers as 0. So we can say that v0, our initial state, will just be 1, right? That's representing the one way to get nothing. And then there's no ways to get negatives, so those will all be 0. And then we can do the actual trick, right? So we want to raise m to the nth power, and then we can multiply it by d. Right, so actually this is supposed to be a column vector with, so v2 is supposed to be on a separate row. And we want vn, which is going to be the first element of vn. Okay, so that's actually the whole solution, and now we just need to implement mostly this function. It will take a few lines, but they're all straightforward. And we are using a type def for matrices. I'm calling mat. So we actually need modular arithmetic. We're doing everything not 10 to the 9 plus 7, that's what I told us. Of course, otherwise the values would be unspeakably large. They're going exponentially for 10 to the 18 terms. Probably the hardest actual part of this is writing matrix multiplication. So just remember, matrix multiplication is a dot product between the rows of A and the columns of B, which means that the length of each row in A has to match the length of each column in B. K. And obviously it doesn't matter what you name them, but I find it easier to think about when I name them this way. Cij plus equals aik times bkj. Right, so this is the dot product, the kth row of A with, sorry, the ith row of A and the jth column of B. The multiplication is actually straightforward by comparison. Or, sorry, the exponentiation. Once you have multiplication, it's quite easy. But that's, right, again, this is where the magic happens, is if the exponent is even, then we can take a squared to the e over 2, and otherwise we just pull off an a. Right, this is the obvious definition of exponentiation. But the point is that this runs in log time. going on? I see. It was indeed the hardest part. Okay. So what is the example? 8 should give 125 instead it gives 0. That is actually small enough to be inside of our pre-computed values, so what happened? A little bit of debugging here. Should be I minus j, right, not dj. Okay. Let's just see if the matrix version works. Does not. Okay. We should multiply it. Right, we were getting b1. You want to multiply mn to get bn. 125, cool. Doesn't really matter how many values we can compute, especially because we're not even using them, as I thought we would need to. But it turns out that it was easy to think of sensible definitions for negative values of d. And cool, so this works. So another example of using matrix exponentiation to solve a linear recurrence, right? First we wrote down the recurrence, then we wrote down our state matrix, we wrote down what we wanted m to be, then we figured out what m actually needed to be to have this property. We figured out some initial state matrix using d0 and the negative d's, which made sense to say that they were 0. Both in terms of like the recurrence and also just in terms of the problem, right? There's no way to get negative numbers by throwing dice, but there is a way to get 0 by not doing anything. And then we raised m to the nth power. We multiplied b0 times nn to get bn, and then we just output the first element of vn, which was dn. And we needed to implement matrix multiplication and matrix power. Exponentation by squaring for the matrix power. This is just normal matrix multiplication. One's an n cubed time. Here n is 6, so that's fine. And the modular stuff, because we are doing the matrix math, mod 10 to the 9 plus 7. And that's the whole problem.